Yesterday, we started talking about vertical circular motion. By vertical circular motion, we mean an object going around a circle still like it was before, but this time that object will go upside down. So we might have a situation where maybe the object, a car, a roller coaster car, is at the bottom of a circle. Maybe it's, I don't know, somewhere up here. Maybe it's somewhere up here. Whatever. Okay, in the end, this car, no matter where it is in vertical circular motion. There's only two places, however, that we have to learn to analyze. The first one is when the object is at the top of the circle, like it is right here. And the second one is when the object is at the bottom of the circle. And the reason we only analyze those two spots is because those are my two extremes. Now, we saw problems yesterday. They weren't all necessarily cars on tracks like the diagrams that I have drawn there. Sometimes it was water buckets being swung in vertical circles, and it was these water buckets on the end of strings. It doesn't really matter. Okay, the same analysis applies whether it's a track pushing on the car or whether it's a string pulling on the bucket with the water in it. And the same analysis applies, except that sometimes we call the normal force that we have in this one the force of tension, if we're talking about the string or the rope. What forces do we have acting on this car when we're at the top of the circle here? What's one of them there? Everett? Good. The force of gravity is going to act down. In fact, the force of gravity is going to act down in both cases, right? Force of gravity always acts down. What's another force that we have acting here? Another force, Taylor, that we have acting here. The normal force. In which way does the normal force act when you're at the top of the circle? Downwards. How big is it? We don't really know. Maybe it's bigger than gravity. Maybe it's smaller than gravity. In fact, there's one situation where the normal force is actually 0. But generally, there's a value. We just don't know what its value is. The normal force at the bottom of the circle, Stefan, which way is the normal force at the bottom of the circle going to point? Upwards, towards the center of the circle, right? And we know that the normal force there is going to be bigger than the force of gravity. Otherwise, it wouldn't stay in a circle. If the net force was downward, then it's not going to stay in a circle. Next step, always the same. For both situations, F net is equal to the sum of the forces, Fg plus Fn. Or if you happen to be dealing with that string with the bucket of water or whatever it is on the end of it, then we might say Fg plus Ft, or we could still call it Fg plus Fn if you wanted to. Hey, what's the next one? This is what separates all those problems that we did in the last unit from what we're doing right now. F net is equal to the sum of the forces, but F net is also equal to what then? F net is also equal to, Olivia, F net is also equal to what? I'm sorry? William? Good. It's mv squared over r. F net is equal to m times a, right? But a, the centripetal acceleration, is v squared over r. So it becomes mv squared over r equals fg plus fn. We sub in our numbers. We solve for what we're looking for. Now, be careful. Okay? We got to pay attention to positives and negatives once we start plugging numbers in. Okay, and the top one, on the top diagram, the centripetal force is negative because it's acting downward toward the center. Gravity is negative because it's downward. The normal force is negative because it's downward. But at the bottom of the circle, what direction is the centripetal force at the bottom of the circle? mv squared over r. Which way does it act? Emma? It's positive because it's toward the center of the circle, and the center of the circle is up relative to where you are. Force of gravity would be? Tori, the force of gravity is going to act which way, positive or negative? Negative, good. It's acting downwards, no matter whether you're at the top of the circle or the bottom of the circle. And the normal force, when you're at the bottom of the circle, is which way? Noah, which way is the normal force at the bottom of the circle? Yeah. Right. It's positive because it's upwards. Good? Plug in your numbers and solve. Okay, yesterday we extended this a little bit to say, what happens if an object happens to be going too slow when it's going around the circle? Well, we know the answer to that question, right? It falls out of the circle. It doesn't stay in the circle like it is right here. Well, then it's not a circular motion problem if it falls out of the circle. It would actually be a projectile motion problem. We're not going to worry so much about that. What we're going to do is worry about that point where it will stay in the circle. In other words, how fast you have to be going to stay in the circle. You guys know that if you're going around a track like this, or if I use my keys again as the example here, if you're swinging the keys around in a vertical circle, if you're going fast enough, it stays in the circle. But if you're going too slow, it falls out of the circle. The Cirque du Soleil video that I showed you guys yesterday, right? When the guy was laying on that wheel of death, right? When he's laying on it and he's going just a little bit too slow at the top of the circle, what happened to him? He fell out of the circle, right? We want to know how fast you need to be moving to stay in the circle, right? The faster the better, but how fast is the minimum speed that you need to be going to stay in the circle? Well, what's the condition that we find is held when an object is going at the minimum speed? In other words, when you look at these keys swinging around the circle, what do you notice? What do you notice happens when the keys are barely going the minimum speed? Like right now, they're barely going around. What do you notice about this? What do you notice about this scenario here? Rosie? Yeah, you know what? That's true. They do actually slow down a little bit when they get to the top. Now, we're going to assume for purposes of these questions that they don't, because uniform circular motion depends upon them going at a constant speed, right? So that's not what's going to be the big deal here. Okay? When they're going at the top of the circle, David? Yeah, there's no tension on the string. So the string doesn't have to pull down, right? As I'm swinging them around at a pretty high speed right now, when it's at the top of the circle, gravity pulls down and the tension in the string pulls down. The normal force pulls down. But when I'm at the minimum speed, watch it. It's just gravity doing the work. The string doesn't have to pull. So you want to find minimum speed? Do this for the top of the circle, but for minimum speed, you want to set Fn equal to 0. So do exactly the same thing, but set Fn equal to 0. So then my equation becomes simply mv squared over r is equal to m times g, and you turn around and usually solve for v. We had a couple questions on that for homework last night, page 262. Which one or ones do we want to go over here? I definitely want to go over at least one of them. We'll go over both of them if we need to. All right, let's take a look at number 2 then. 2 is a little bit different, right? It doesn't say what's the minimum speed. It says what's the maximum radius if you're going around at this speed. Well, it's kind of the same thing though, right? If you're swinging these keys around and there's a certain minimum speed that you can travel, all right, that's great. Set Fn equal to 0. But if you're going more than the minimum speed, you can imagine if I increase the radius of the circle, there comes a point when it's not going to make it all the way around the circle. Right? So let's say you're going at a certain speed that at a smaller radius would be more than the minimum speed, but then you increase the radius to the point when it falls out. What's the maximum radius that you can go to not fall out of the circle? We're going to do exactly the same thing. We're going to analyze the circle at the top. The normal force acts down, the force of gravity acts down. The net force is equal to the sum of the forces, Fn plus Fg. mv squared over r is equal to Fg. We're getting rid of Fn because just like at minimum speed, at maximum radius, the normal force will be 0 as well. Cancel out m's, stub in our numbers here. We know what v is this time, 20 meters per second, square it, over r equals 9.81. Now, technically, both sides should be negative because both forces are acting down. But in this case, because in every term, you can cancel out the negatives, and if you forget them altogether, then it still works out. Okay, the r goes up by multiplying. The 9.81 goes down by dividing. When I say r is equal to 20 squared divided by 9.81, r ends up being equal to 40.8 meters. So, if you've got, say, a roller coaster, you want to make sure that for a particular radius, you want to be going a certain speed. You want to be going over a certain speed. Or if the roller coaster happens to be traveling at a particular speed, you want to make sure the radius is under a certain value. So you're going to have a minimum speed at which you can go around, or a maximum radius at which you can go around. Right? We had a couple other questions for homework as well, and those were on page 268, questions number 6 to 10 on page 268. Let's take a look at those ones as well. The two questions that we want to go over from page 268, number 6 to 10, are questions number 8 and questions number 10. Let's take a look at number 8 first. It says, this is a different question than we've just been doing, right? This is not a vertical circular motion question, but that's okay. It's good to go back and review a little bit of that old stuff, the stuff that you're going to see potentially on your quiz tomorrow. A 1,500 kilogram car is making a turn with a 100-meter radius on a road with a coefficient of static friction of 0.70. What's the maximum speed that the car can go without skidding? Well, listen, if this car is going around in a circle, there is a centripetal force. But forget about that for a second. What is it that causes the car to go around in a circle? In the absence of this force, this car will go off in a straight line. What force am I talking about? Friction, right. It's centripetal force, but really that centripetal force, it's just friction. We're just applying another name to it, right? Renaming it the centripetal force. We're going to say the centripetal force equals the frictional force because they're really one and the same. mv squared over r equals mu times the normal force, but the normal force, as long as we're on a flat horizontal surface, is m times g. So we get mv squared over r is equal to mu times m times g. We've done a couple of questions like this before, right? We've seen that the mass cancels out. Hey, if the mass cancels, then that tells us that it doesn't matter how heavy the car is. You got a light car, the smart car going around the turn, or you got a big semi-truck going around the turn. Doesn't really matter. Semi-truck can't go quite as fast around a turn because it might tip over, right? It's a little top heavy. Okay, but it has nothing to do with friction. In the end, theoretically, a heavy car can go around the turn at the same speed as a little light car can. It has the same tires on it. All right, we're looking for speed here. The radius is 100 meters. The coefficient of static friction is 0.70, and g is 9.81 meters per second squared. We're not going to make either of these negative. Okay, this equation looks quite a bit like the minimum speed equation that we just saw a few minutes ago, but it's not the same thing. These are always going to be positive. V ends up being the square root of 0.70 times 9.81 times 100. We get a final answer rounded to 2 digits of 26 meters per second. So what happens if you're going 25 meters per second? No problem. Stay on the road. 22 meters per second? No problem. Stay on the road. 27 meters per second? Friction is not big enough anymore. You're not going to go in a circle because that friction can't supply the centripetal force necessary to keep you in a circle. Next question was number 10. It says NASA uses a centrifuge that spins astronauts around in a capsule at the end of an 8.9 meter metallic arm. We did a question earlier on when we talked about a centrifuge spinning blood around. You remember that one? Separates the blood. The heavy things go to the outside, not because of centrifugal force, but because of, what's the I word that takes something to the outside of a circle? Not centrifugal force, but rather it's inertia, yeah. And the reason that it separates that blood into its components, the heavier components to the outside, is because the heavier components have more inertia. Inertia is dependent upon mass, right? Well, NASA does the same thing with astronauts. Why would they do that with astronauts? Well, it's like the gravitron ride at the Stampede, right? When you're spinning around and you want to go in a straight line, you feel like you're being pinned against the outside. The centripetal force pushing you in makes you feel like you're heavy, makes you feel heavier. So they spin astronauts around in these centrifuges. It's like a gravitron ride, basically, except they can spin it faster to simulate intense gravity. Hey, we're used to 9.81 meters per second squared, but on takeoff, an astronaut might have to withstand 4 Gs, 5 Gs, not 9.81 meters per second squared, but 40 or 50 meters per second squared for a relatively sustained period of time. They need to be trained for that, otherwise they're probably going to pass out. So this is what they do. They use this centrifuge, spin them around, make them feel like they're 4 or 5 times heavier than they really are. They do that with fighter pilots, by the way, as well. Centrifuge spins at 35 RPMs. We don't want revolutions per minute, right? We want hertz. We want to find the magnitude of the centripetal acceleration that the astronauts experience, and how many times greater is this acceleration than the acceleration due to gravity. All right, we got a radius here of 8.9 meters, and we have a frequency of 35 RPMs, but we're going to convert that to rotations per second, or hertz. How are we going to do that? We're going to multiply by 60 or divide by 60 there? Rotations per minute, rotations per second. Multiply by 60 or divide by 60. What do you say there, Natalie? We're going to divide, right? You're going to have less rotations in a second than you do in a minute, right? 35 divided by 60 ends up giving me, convert that to hertz, we get 0.58333. Ideally, we have the completely unrounded number, but 4 or 5 decimal places is okay. What do we want to find here? We want to find the acceleration that the astronauts experience. It's a centripetal acceleration, right? So let's say A is equal to V squared over R. We don't know that, so let's figure it out. V is equal to 2 pi R over T. 2 times pi times 8.9 over, we don't know T either. So let's get the period here. It's 1 over 0.5833. What does that equal? Good, that's good enough. So we divide that 1.714, and Rosie, what do we get for the speed there? I'm sorry? 32.63? All right, 32.63 meters per second. That's pretty fast, actually. So you're going at highway speed, right? Speed you'd be traveling on the highway, except you're in this little metal box spinning around only with a radius of 8.9 meters. That's pretty fast. 32.63 meters per second. Let's square that. Divide it by the radius of 8.9. I think we're going to get somewhere around 100, aren't we? What is that final answer? We're going to be 32 squared divided by 8.9. You get 102 meters per second squared, which really, you gave it to me in scientific notation, Rosie. It really should be, because I should be in 2 digits here. 1.0 times 10 to the 2 meters per second squared. Wow, that's a big acceleration. 1.2? So it was 120? Thank you. Even more. It's an even bigger acceleration, right? What's gravity? 9.81. How many G's does this person experience? Well, the number of G's, you're going to have to do this, by the way, on your West Edmonton Mall Museum Park physics assignment that's coming up on May 31st. You have to do this lots to find the number of G's. What are you going to do? We're going to take the acceleration that you found, which is 1.2 times 10 to the 2. We really should have our unrounded number there. I just don't know what it is. And divide it by 9.81. We do that, and I think we're going to get about 12. 12 G's in this centrifuge at NASA would cause pretty much anybody, probably anybody, to pass out. Okay, you're not going to experience 12 G's and stay conscious. Okay, the good news is when you're taking off in a space shuttle or something like that, you don't experience that many G's. Even a fighter pilot doesn't experience that many G's.